talk of the annual lecture series here at the Center for Philosophy of Science. Today it's a great pleasure to welcome Andrea, who is a professor of philosophy at the University of Washington. Andrea works in many areas of philosophy, general philosophy of science, with a focus on representation and explanation, but also philosophy of chemistry, but also aesthetics and feminist philosophy of science, and more broadly feminist philosophy. She's also, and we should thank her every day, so the editor of Philosophy of Science, which is quite a lot of work, so we should be very grateful that she's doing this service for the profession. And today she's going to be talking about smart search. Oh, I forgot to say, she also has a PhD from the University of Pittsburgh. So welcome back. And today she's going to be talking about smart search through complex landscapes.
Thank you so much. It is always a great pleasure to be back in Pittsburgh. I remember my time here with great fondness, and I learned a tremendous amount from many of the people in the room. So thank you for having me back, and I'm looking forward to sharing some initial thoughts on a project that's ongoing for me. I will say that this is something that really is a work in progress. And one of the reasons why I was happy to be able to speak with you about it today is because I'm really eager for feedback. This is a project that has come through a collaboration that has been funded by the Templeton Foundation. So it's a group of scientists. It's being funded through what used to be in the Templeton Foundation, the Mathematical and Physical Sciences Division. And they were encouraged to bring a philosopher on board. And that's how I became connected with the project. So one of the reasons that it interests me is because I think that it's an example of what hopefully will become a more common situation in which philosophers are really working hand in hand, or sort of sitting in on ongoing scientific work and trying to offer insights and thoughts about that work that might actually be helpful to the scientists that are doing it, give them different perspectives on the work that they're doing. So, to get us started, I think there are two broad perspectives on science that we see in the philosophical literature. I'm not claiming there are only two, but these are two rough glosses that give us just an initial scaffolding. The first one is we can think about science as reading or writing, depending on your orientation, the book of nature. And under this general way of thinking about it, we're often thinking about the primary project as assessing the epistemic status of the hypotheses that are generated in science. And the aim of scientific activity is often considered generating veridical representations of various empirical domains. And so this is a view of science that sees it as essentially representational. Now, there's an alternative to that, which sees science as a toolkit for control, intervention, production of effects in various empirical domains. And this is a much more thoroughly pragmatic enterprise, and it's aimed at action in the world, doing things. Right? And I don't see these two conceptions as being necessarily in tension with one another. They're complementary. But I do think we have a longer tradition in analytic philosophy of science of looking at things from the first perspective than from the second. Now, quick example of the difference between the two perspectives. If we think about predictive capacities, right? From the first perspective, we might look at a successful prediction as a means of giving us evidence, right, for the various hypotheses that we have on the table. And so, for example, the debates about the difference between prediction versus accommodation, right? That's about epistemic status and about the sort of evidence that we get through successful prediction. On the other hand, you can look at prediction as a tool for intervention. So, for example, if we make predictions about climate change, and we take it that those predictions have a good chance of being robust, then we may take action, right, to mitigate, for example, harmful effects of climate change. Now, OptiSci is a project that's been funded through the Templeton Foundation, and I'm going to I'm going to describe this project for you, and then I'll return to these broad perspectives towards the end of the talk. So, OptiSci, and that's the title that has been given by the group to this project. It's a project where the assumption is that we're looking at optimization goals across a broad range of scientific domains. And we're looking for optimization where the possibility space that we're trying to search or consider is often quite large, and often where the available data about whatever property we're trying to optimize is quite limited. So the challenge is we'd like to do a rational search of the possibility space, and we want it to be directed rather than just random, right? Usually because we'd like it to be more efficient, right? There are going to be various material requirements if we're trying to obtain an optimization goal. So for example, a case that we'll look at in a minute, let's assume that we'd like to synthesize a molecule that optimizes a particular property, right? Maybe its catalytic property or its ability to inhibit the function of a particular protein, right? If we're not sure which molecule would optimally obtain the outcome, every time we have to synthesize one and test it, there are all sorts of material conditions at play. So we have to spend money, we have to spend time, right? We have to spend human capital. If instead we try to implement the search computationally, then we have to deal with whatever our existing computational capacities, right? So what algorithms do we have that might be feasible to implement? Now, the strategy that OptiSci tries to employ is that it uses an overarching framework, a formal framework that we'll talk about in a minute. It wants to implement search by using computational algorithms, and it's very opportunistic. So it would like to be able to operate robustly even with limited requisite data and very little background knowledge about the spaces that are being searched. Now, there is a formal framework that stands at the heart of OptiSci, and we'll talk about that in a minute, but it's currently being applied in 3 different domains. In OptiQ, that was the original realm in which it was applied. So the person who's the PI of this project, Herschel Rabitz, is essentially a chemical physicist who works primarily through formal means. So there's a formal framework that's being applied to optimize certain outcomes with regard to quantum phenomena. And in most cases, this is through using shaped laser pulses. Right? Then there's Optichem, which is looking to optimize, really, there are 2 strands of Optichem. One is trying to do efficient search to synthesize new molecules or new molecular constituents, and the other is to optimize properties that may be desired in particular molecules. And then there's OptiEvo, and OptiEvo, that strand is looking at optimization in the context of directed biological evolution, primarily bacterial evolution. Now, I'm going to be talking primarily about Optichem today in terms of the details. So it's a subset of OptiScience, and here's a general characterization of what we're going to be trying to do. So we want to consider chemical goals such as achieving high synthesis yields or optimizing the properties of synthesized products. And we want to consider them to be optimal control problems, in which one seeks to optimize some target objective in relation to a set of identified variables. So the variables in these cases are going to be things like the various reagents that I have, right, in order to have a chemical reaction go through, or the particular molecular scaffolds that I have for building a particular constituent, as well as mechanical factors like the thermodynamic properties I have to work with, under what temperature constraints, etc. Now, the general strategy that all of OptiSci uses, but we're going to see it in the context of Optichem, is to construct a chemical property landscape that represents the relevant space of possibilities. Then we want to analyze that landscape topologically to identify the optimal product or outcomes that are desired. Now, this is going to be implemented via an automated search of the corresponding landscapes. Obviously, there are lots of ways to implement that search. In Optichem, well, in fact, in all of OptiSci, the goal is to use what we call, local search techniques rather than global search techniques. So, in general, as we're trying to search a space to find an optimal result, in any case, we are sort of doing local searches throughout the landscape. That's because under conditions in which local searches can be implemented, they tend to be considerably more efficient. We could, however, use global search techniques that are often stochastic, right? They can be robust in circumstances where local ones aren't, because they can often get you out of traps, right? So if you're sampling a space very widely, but they tend to be less efficient. Now here's just one example to help you think about things in this way. So there's a product, and we're trying to, in effect, optimize the yield of this product, right, which is a 1-glycerol monooleate. And this is a landscape that shows we've got two variables in this case, a temperature variable and the concentration of a catalyst for the reaction. Right? Our goal is to maximize the acid conversion, which generates our product. Here is the landscape of outcomes across those two variables. And we're going to talk about this graph in more detail in a minute, but this landscape is a combination of experimental results. Those are things that we know. Those are the hard dots on the graph. And then we've curve fitted effectively to generate the rest of the landscape. Now, the challenge is that the possibility spaces that need to be searched are often quite large and of high dimensionality. Right? So every time you add a variable, you're adding a dimension to your space that has to be searched. Right? Often the variables themselves, sometimes they're continuous, sometimes they're discrete, but in many cases they're quite large. Just in terms of the number of options that we have with regard to individual variables. The automated search procedures, in order for those to work, you need a landscape that's actually amenable to exploration. And if you want to use these local search algorithms, then the most important thing is that you don't have traps. Right? And so we'll talk about that. One of the ways in which we try to set up a circumstance like this is by employing the formal framework that rests at the center of OptiSci. So now I'll say a little bit about that. So I'm going to talk today because my concerns aren't primarily the formal results. I'm going to give you them conceptually, but the two papers that present the work rigorously are given here in case anyone wants to take a look at the details. Right? So the formal framework basically is just a set of 3 assumptions. Right? And the assumptions are relatively simple conceptually. So the first one is controllability. So we assume that there is, in fact, an optimal solution for a given set of control variables. Right? That seems like something you need to assume to even get the whole project up and running. We assume surjectivity. Right? So this is what guarantees that local movement on the control landscape is essentially smooth. Right? That we can do the search using local search techniques. And then we assume that our resources are generally unconstrained, that we have adequate controls in the system to actually be able to locate the optimal point, whatever it is. And that'll end up being important in a minute. Now, the result is formally characterized. Part of what can be proven is that the corresponding landscape is almost always trap-free. There are some few, small number of cases where we actually can't guarantee that such a landscape that accords to these 3 assumptions will be trap-free, but it's essentially measure 0. So it's a very, very small set. Now, let's go back and see how this works with regard to some examples in Optichem. And the first one that I want to look at is a technique where, in effect, using the OptiSci framework leads to increasing the number of dimensions that are being employed in order to construct a landscape. So this is the example we looked at just a minute ago. And if you look at this example, one of the things that might hopefully be obvious to you is that there are some traps in this landscape. So there are some holes, right? So we're trying to get to the optimal result. Who knows exactly where it is? We'll find out in a minute, but somewhere over here. You can see that what would happen is that if you ended up in some of the points of the landscape and you're employing a local search algorithm, that you're likely to get stuck. Right? So here's what the group actually did. They added another variable to the set. So originally, we were looking at just variations in temperature and variations in the concentration of the catalyst. And we're looking at the percent conversion to the product under a fixed reaction time of 300 minutes. Now we change the reaction time, we make that itself a variable, right? So now we've moved from essentially, right, this three-dimensional landscape, well, it's a two-dimensional landscape for the relevant variables, to a three-dimensional one. So we've added time as another variable. And then this gives you the percent yield in colors now. It's a little harder to see, but you can see that the dark brown, you can see our optimal result is somewhere in the neighborhood of this big brown spot. Right? It turns out that that's a smooth landscape, and we in fact can show that it's a smooth landscape without any traps. It's trap-free in a way that the lower dimensional landscape was not. Now you might be thinking, so what's going on? How does OptiSci relate to this? Well, let's back up just a second, right? The third assumption was that the resources are unconstrained, that we have adequate controls to find the optimum. What's going on in this case is that we look at a given system, we find traps, the framework says there should be a trap-free landscape. And so in effect then, the scientists are given the push to go looking for it. What's another variable? Can we find a way to convert a system that we can't search using the techniques at hand into one that we can search, right? And adding dimensions is one possibility. Now, this is interesting because, right, in most cases when we're trying to implement things computationally, the natural inclination of the researcher is to assume that increasing the complexity of the representation of the system is going to make computational techniques harder to implement rather than easier, right? But in fact, it turns out that in many circumstances that's just not the case, right? So here are the two just so you can see the difference. Now here's the second one, and this one is more interesting. This is a reordering algorithm, and I'll explain in just a second what's going on here. So here's what we're going to do. Again, we have two variables, and we're trying to optimize some property of a given molecular system. We have two variables, x1 and x2. The reordering algorithm basically says, take this landscape, and then treat it effectively like a Rubik's Cube. Reorder either variable in such a way that you ultimately produce the smoothest landscape that you can. So what we've done is we take columns and rows and just shuffle them in order to smooth the system. So we turn data that look like the first landscape into the second. And unfortunately, there actually should be a gradation there that would make it easier for you to see, and I'm sorry that it's not showing up here, but I'm going to give you a case that is a little bit easier to see. So now, here's a case where the reordering algorithm is being applied to generate predictions about the NMR shift that would happen in a molecular system based on the functional groups that are included on a scaffold. So if you look at the up at A, we have a simple molecular system, a simple scaffold, and we're looking at the C13 shift at the point that's pointed to in the, on the left-hand side of my scaffold. And I'm creating molecules that have a variety of functional groups at site X and site Y. And these are my possibilities. There are 15 of the things I can stick on the end, right? Now, initially, I construct a landscape simply by, for these variables now, of course, they're discrete variables, X and Y, because they just range over these 15 possible molecular chunks. We order them randomly. You order them any way you want to generate the landscape, and you get the landscape at the top. Then once you have the landscape that essentially has been generated through arbitrary arrangement, you use the reordering algorithm to smooth, right? You produce the smoothest landscape you can. And in fact, what you get in the purple, if you can see these, you can see now this is the new ordering, and above it was the original ordering. So you can see how things have been shifted. Now, why is this important? Well, if you look at the first landscape, right, with the arbitrary ordering, and then what you do is you try to interpolate, you make predictions of the NMR shift for the molecular entities that you haven't tested yet, right? So the ones that are white. And you test them. Here you get the truth plot for the experimental shift versus the predicted shift, right? And you see the scatter plot. If you reorder the algorithm, if you employ the reordering algorithm, and then go through that process again, so you interpolate, essentially, the values for the unmeasured data, and make those predictions, this is the result you get. Now, imagine that what you are trying to do is you're actually trying to design a molecule that has a particular NMR shift, right? If you're in a circumstance where you can generate this landscape, you're in a much better position to predict which molecule ultimately will have the shift that's the desired shift, and then you can take that into the lab, right? Or at least look at a small set of them. So it potentially increases the efficiency of the search. And the other thing that's interesting, and here I'll give you a quote. This is work that is being done by Catherine Moore Tibbetts. So she's my primary collaborator because she is the lead person in the Optichem portion of the group. And I'll give you just one quote from this paper. She says, the chemical shift landscapes revealed by NMRscape, these constructed landscapes, can confirm previously established empirical rules relating chemical shift values to molecular structure, as well as to uncover otherwise hidden relationships. Right? So part of what we see is that when we employ a technique like this, we can recover some of the general relationships that we already know exist in terms of what the impact of various functional groups have on the shift in the NMR signal, but also potentially can discover ones that haven't been determined yet. Right. The other thing that is really interesting about this technique, and this is something that is relatively new, is that it turns out you can improve the efficiency even more if you implement the reordering algorithm iteratively. So what you do is, if you've got some set of measured data, you take a fraction of your measured data. So the ones that you know, you take a fraction of those, you reorder based on that fraction. Then you add in a small, subset of the additional ones that are left over. Reorder again. Again, reorder. It turns out that you can ultimately find the desired results more quickly. And so here we can see this is a different problem where we're looking at the impact of putting two things on a scaffolding that's cyclical. Here's our measured data. We optimize to generate the best landscape we have. Then we add in more data, repeat the process. Now here's a case where it's actually been done. So the first one is the row. So this is now, these are the results from trying to construct a case where we have a goal of inhibiting a certain protein from activating. So we're looking for molecules that would have maximal inhibition properties. Right? Now, this is random ordering. We are looking at a case here. We've got 2 sites on a long molecular scaffold that remains the same throughout. We have 2 sites on which we're putting various constituents. We've got about 150 constituents possibilities on the one site and about 100 on the second site. Right? So we have about 15,000 molecules that are possibilities here. Now, if we look at this molecular library, this is random ordering, right? Then we use 25% of the known data to generate the reordered landscape. That's what you get in the middle. Then we add in the additional data to see, in effect, how well we've done, right? And then this is what we get by adding in the data that we didn't even use in constructing the original landscape. Now, this was actually implemented. This is a case where ultimately it was implemented iteratively. And what they found was that if we used, and let me pull up the data to make sure that I get this right. So what we're trying to do is, the goal here is to find 90, right, to be able to locate 90% of the known molecules that have that have at least 70% inhibition on this scale, and we're trying to figure out how long it takes us to find them. Right? If we use the iterative technique that was ultimately employed, right, we would have had to have synthesized 650 molecules in order to find the set that we wanted, right? This was originally implemented in a lab, right? So this work was done prior to the Optichem people coming in and analyzing the data set, right? And they were doing random search, right? And it took them 2,500 syntheses in order to find the same set, right? So the set size was reduced by an order of 4, right? So a great improvement. Now, a couple things are noteworthy about the Optichem results to date. Right? First, there's often this worry about what's called the curse of dimensionality. That as soon as you try to represent systems in their full complexity, that what's going to happen is that computationally you're going to get stuck, you're going to get clogged down because of the richness of the possibility space. But in fact, what we find is that often higher dimensions lead to more tractable landscapes that then we can use, in effect, more efficient search algorithms on those landscapes. And so there ends up being improvements. That iterative reordering often enhances the efficiency, and it is worth stating that we have a relatively small set of cases that we've tested, right? So Catherine now has about 400 data sets that have been tested using the reordering algorithm, and the results are highly impressive. But still, it's 400 sets, so I don't want to overstate the case here. But in those cases, there are no cases in which the iterative reordering ends up being detrimental, right? And in about 75% of those cases, the iterative reordering ends up increasing efficiency fairly dramatically. The other thing is that this whole process works under relative ignorance, right? Because I start, right, we're assuming in these synthesis cases that the variables largely are molecular constituents that are going to be attached to a particular site, right, in a larger molecular framework. And the possibilities, are some set of molecular constituents. And so the variable is a discrete variable. There's no obvious way to order the possibilities within that variable. So it's just done randomly initially, right? There's no chemical knowledge behind the setup of the system, right? It is the case that it does seem to be that chemical knowledge, in effect, is reflected in certain regards in the results, but it can be implemented without having to have really deep knowledge of chemical patterns on the front end. That's not, of course, to say that you couldn't possibly use that knowledge in tandem with these techniques to increase your efficiency even further. So I'm not making that. So in effect, right, OptiSci, I think in the most general terms, and so this is of course where the title for the paper is coming, it's smart search through complex landscapes, right? In part by trying to figure out often how to construct those landscapes in the appropriate way to make them amenable to search in the first place. Now, things to highlight about the OptiSci applications. First, there's coupling of diverse methods we'll talk about in just a minute. The impact of the landscape perspective that's being used, and the fact that there's a unified formal framework that is essentially the grounding that then gets the whole machine up and running. And I want to look at each of those just briefly. So first of all, in terms of coupling the diverse methods, we have a formal framework, then we have various computational and numerical techniques. Those include things like the reordering algorithm, and then also the search algorithms that get used. So there are different types of computational techniques that are employed here. And then there's directed experimentation. So obviously, you then have to use experimental techniques to confirm and often to do the final steps of the search process. But they're in effect, they're conjoined, right, in an interesting way. So it's a primary example of what I think in philosophy of science we often call mixed methods, right? There's this dance of the formal and the experimental with the computational that all have to work in exactly the right way to achieve these results. Right. Then I want to talk a little bit about the landscape perspective, right? It's a choice of conception and of representation. And I think it'll be obvious that you don't have to think about optimization problems in this way. They don't have to be conceptualized as landscapes. This is a choice that's been made. Now, of course, right, and I think it's important, mathematically, formally, we can represent all this information, never have a graph, never see something that looks to us like a landscape, right? So the claim here is not, that we have to represent things in this manner, but it is to say that resting underneath the work is a certain conceptual orientation to the problem that says we have a possibility space, right? And then we're going to create the complete possibility space and then try to figure out what smart search looks like in relation to that space, right? And again, when you think about something like, I just want to build a molecule that has a certain capacity to absorb energy at a particular wavelength, right? You don't have to think about that sort of problem using these basic conceptual resources, all right? Once you do choose the landscape perspective, that structures, I think, the way in which you think about the specific challenges that these sorts of problems present, right? So, and that in turn spurs the development of particular techniques. So, for example, if you have a formal framework that you've decided to apply, and the formal framework says there must be a smooth landscape, there must be a trap-free landscape, then when you look at our first example where we added a dimension, if you find a landscape that has a trap in it, right, then of course it becomes natural to say, like, well, maybe there's another landscape that also represents the system that would be smooth, because my formal framework said there should be one, right? So then the move to say, maybe I need to add another variable, becomes a natural move. Similarly, the reordering algorithm, right? I mean, it's a Rubik's Cube maneuver, right? But it's a maneuver that in some sense is being underwritten by an assumption of how we're going to conceptualize these problems, right? That then pushes the development of these computational techniques in a particular way, right? And ultimately, it facilitates discovery and prediction, right? So, and in that regard, these results have generated a lot of excitement, because the optimization problems that often face chemists today are ones where, for example, we're thinking about very large chemical libraries. Right? So imagine you're a drug development company and you've got a library that has, right, hundreds of thousands of molecules in it. And you need to try to figure out which one's going to be efficacious for a certain medical use. And you're Pfizer, so you need to get there first, right? So you need to find the optimum, and you need to be efficient about it, right? And so smart searches end up being incredibly valuable in that sort of landscape, right? There are also cases where the fact that these techniques often lead to some robust predictive capacity. So if you remember the truth plots, from one of the reordering cases, that actually ended up being very useful by the EPA that was trying to figure out drug toxicity. And the problem is, you don't generally want to have to give the toxic chemicals to the people or the animals in order to figure out they're toxic, right? You'd like to limit the amount of that has to be done. So if you have a robust prediction machine that can help get you the information you need reliably without having to implement more of it through direct experimentation, again, that's a valuable product. Right? Let's think about it just a little bit in terms of going back to this protein case. Right? So in this case, we've got a case of protein engineering, and this actually is a case that originally was implemented by Pfizer. Right? There's a large library, although it's actually a pretty modest library by chemical standards. So you've got 15,000 possibilities. And transforming the landscape actually meant that then the researchers could concentrate on one limited area of the landscape. Right? Conceptualizing in this way, right, conditions what to search for and how to search for it. It says to eliminate traps, to think about ways to do that. It says when you have discrete substituents, right, it suggests the reordering algorithm that allows you, in effect, to discover patterns. Right? It facilitates discovery and prediction in part because it narrows the range of possibilities. So again, there's sort of this interesting meshing of techniques. It's also a framework for unification, and this is a part that I'm still grappling with, but I think is one of the most interesting aspects of this work for philosophers of science. Right? So we have a framework that's general, that's abstract, that's overarching. We've only talked about Optichem today, but we could have a similar talk about OptiEvo and about the work that's being done in that context, for example, to think about ways to grapple with antibacterial resistance, right, by turning smooth landscapes into jagged ones. Right? Part of the problem is that genomic landscapes, because there are so many variables, tend to be actually very smooth. And that's one of the reasons why fast evolution in certain circumstances seems to be quite viable. Or we can talk in the quantum cases, but we haven't done that. Right? There's sort of a dual functionality to the formal framework, it seems to me. It's scaffolding for tackling these optimization challenges, and in that regard, it's optimization that's being used as a method. Right? Lurking in the background, inevitably, is also another way in which the framework is functioning, which is an assumption regarding the orderly nature of the domains that are being searched. Right? And so that is an aspect of unification that really is about claim about the way the world is. So if we go back, right, so we started off with me saying, like, there are these two broad perspectives, right? Science, right, as giving us a veridical representation of the way the world is, and science is about acting, right, about being able to intervene in the world in productive ways. Well, I think those two broad perspectives actually capture this dual operation of the formal framework, right? And I mean, I'm tempted. I will say that in my conversations with the PI, right, who's had a long career as a theoretical chemical physicist, works primarily in terms of formal methods, and so has a lot of faith in the strength of those methods to reveal things about the world. Right? He looks at OptiSci, and you know, if I'm speaking bluntly, right, he sees the bones of the universe, right, the hard structure, right, sort of glistening and simple and beautiful. Right? For those of you in the room, you're going to immediately understand why one might be hesitant about that sort of optimism, right? But, right, so, right, I think there's a way in which we might say, well, what's going on here? Well, it's epistemic overreaching based on implicit metaphysical assumptions that lack clear justification, right? Why assume that that framework is going to hold, right? The three, let's take a look at the, oh, actually, I'm a little ahead of myself here. Well, I'll come back to it in just a second. We'll get it, right? I think there are good reasons if your intuitions pique that kind of response to what's going on. At the same time, right, there's this strategic activity that seems to be enabling very fast learning, right? And it might potentially hold the possibility of informing the viability of various metaphysical assumptions, at least in certain contexts. Right? One more step here, right, which is that if we think about the two broad perspectives, and I can't defend this today, so this is just, you know, throwing it out there. I think there's a way in which they map onto another very classic distinction in philosophy of science, which is this notion of reading the book of nature. That aligns very nicely with what we call the context of justification. The game is gathering evidence, trying to figure out how we're going to talk in meaningful ways about the evidential support that we have for various hypotheses. Right? Because that's what we need to assess the potential accuracy of the representations. Right? But then science's toolkit, right, that aligns very nicely with what we call the context of discovery. Right? That's the thing that, you know, if we did early 20th century philosophy of science, we were supposed to learn we can't do. There's not really anything to be said about that. Right? But I think it is undeniable that whatever is going on in a case like this, right, what we see are methods for learning, methods for discovery, methods for search, right? And there's every reason in the world to believe that philosophers could add a lot to the understanding of how those methods work. Right? In part, if for no other reason, then, you know, we can be the slightly skeptical voice in the corner when the overly optimistic conception of why it works seems potentially like the obvious one to some of the players in the room. Right? So, right, here are all the pieces. Again, OptiSci, as the PI conceives of it, is largely held together by this formal framework. So let's go back to that for just a second. Right? And think about it. They're very simple assumptions on some level, but they're also incredibly strong, right? So so you assume there is an optimum. You assume, right, that in fact there is a smooth landscape in which that optimum can be embedded, and you assume that you've got all the resources you need to find it, right? Well, if you granted yourself those three assumptions, right, the result is not very astonishing, right? Because you baked it in, more or less, right? But I think what's really fascinating is that these very strong assumptions, right, when laid down on real problems in empirical domains, have been incredibly valuable in the development of much more local techniques that have aided the solution of optimization problems. there's one other hedge that I should point out, which is, of course, the formal framework is actually a framework that says, right, there is an optimum, right? So it's assuming there's a global optimum. In all the empirical cases that we've looked at, of course, there is no guarantee that the thing that's been found, right, or the set of things that have been found, and then, we declare victory, actually include the global optimum. I think there are good reasons to believe that probably they do, but usually, right, it's indeterminate because the space has not been fully sampled. Right? So on some level, the application of the formal system is being facilitated by a subtle shift in the nature of the problem, right? So the formal problem is find the global optimum, right? The empirical problem is usually find something that's pretty damn good, right? And good enough is good enough, right? And that is different, right? And I think, when we think about this, a couple of other things that I'll point out is that one of the things that I think really requires more analysis and that I haven't done, but I'd be really happy to hear what people have to say about it, is just an assessment of exactly how strong a requirement surjectivity is in these sorts of cases, right? And how to assess that requirement of basically local smoothness. Okay. I'll point out, here as we get to the end, that I think inferences run in both directions in this work, right? So, in lots of ways, right, if we assume the formal framework, then we use that to infer that there is a smooth landscape, right, for representing the problem at hand. And then when we find a relative optimum, we assume that it must be pretty close to the global optimum, right? There's a way in which the formal framework is being used to infer things about the empirical domain. But it is also the case that in the work that we've seen, part of what's going on in the work that Catherine has been doing is she's looking at empirical data sets that have been published under other contexts, and then she's using the machinery of OptiSci to rerun that data and to see if she could have found optimal outcomes more quickly than the original work, if they were also set up as optimization problems. And then when she has success with that project, right, it's being used to say, so it looks like the world probably does abide by, or at least approximately abide by, the three assumptions. Right? So that's a way in which the empirical work is being used to provide some support for the application of the formal framework. Right? So here's just a couple quotes from her that sort of betray this interconnection. Successful construction of monotonic landscapes expressing the chemical shift value in terms of 2 or 3 variables would indicate that the variables adequately describe the underlying chemical shift landscape. And, we could read this in a variety of ways, but I think that it's clear that she intends by chemical shift landscape, she intends to be referring to something that's empirically out, right? There's something that exists. There's an empirical fact of the matter about what the chemical shift landscape looks like. Right? It's not just a conceptual fact. Here's one more. The presence of a trap-free fitness landscape provides an organizing principle for explaining why synthesis and product discovery is far easier than the apparent complexity of such problems would suggest. Here, for those of you who know some of my other work, you'll know why I have to pull out this quote, because of the appeal to explanatory power, right? So the sense that being able to apply these techniques successfully ultimately is going to give us some explanatory resources, right, with regard to making sense of the results. And I think we will we will end there. I want to thank the entire OptiSci team that I've worked with. So Catherine Moore-Tibbetts, she's the one who heads the Optichem and the one I've worked with most closely. Herschel Rabbits is the PI of the project at Princeton. And then these are the other members of the team. So thank you.